Our next section, 2.6, is about a very important class of operators, namely projectors or projections, that will play an important role in the following weeks. But before we can speak about projectors, we need to speak about direct sums. Okay, so what is a direct sum? Well, we will start even earlier with a sum. So let's take two subspaces U and V of one vector space X and look at the following construction. We take the set of all elements that can be written as U plus V, where U is running through U and V is running through V, and call that set, or abbreviate that by capital U plus capital V, and this is what we call the sum of U and V. Here's the first little lemma. This new set U plus V is again a subspace of X. This is not difficult to show. Please try that on your own and ask in the problem session if you have problems with that. Let's look at examples. As a first example, take the space X equal to R3 and put U equal to the set of all vectors that have the following form: X, Y, 0, where X and Y are running through the real numbers. Now this is obviously the XY plane, and let's agree on the following short notation for this. Let's just write vector star star 0, where the star marks the place where you can put arbitrary entries. The two stars are independent of each other, and 0 means 0. Okay, and in the same short notation, let's put V equal to 0, 0 star. You know what that means. It's the set axis of your R3. Well, maybe it doesn't hurt to spell it out one more time. Okay, now what is the sum of these two spaces? So U plus V is the set of all vectors that can be written as a sum of this kind and that kind. Okay, but by adding two of these vectors you can achieve every vector in R3 that is possible. So your sum is the whole of R3. Well, let's give an example. The vector 1, 2, 3 can be written as an element from U plus an element from V. And it's also easy to see that this is the only way you can write this vector 1, 2, 3 as a sum of an element from U and an element from V. So there's no choice here. Well, in contrast, let's look at a second example where we take the same space X equal to R3 and we decompose it into U, which is again the XY plane, and V, which is now more than just the Z axis, it is the YZ plane. Okay? And so now V is even bigger than before, so the sum must be bigger than before or just the same, but more than R3 is not possible. So it turns out that U plus V is again all of R3. So let's take the same vector 1, 2, 3 and decompose it into a vector from U plus 1 from V. But now you say, hang on, this is not the only way you can write this. It would also be possible to decompose it like this, or maybe like that, or in infinitely many other ways, because no one is telling you how to spread this 2 between these two stars, so you could divide this as you like. So we can summarize that in example 1, every vector of R3 has a unique decomposition into a vector from U plus a vector from V. Whereas in example 2, such decompositions are always non-unique. Now this leads us to the next definition. The sum U plus V is called a direct sum, which is denoted by U plus V with a circle around the plus sign. If every vector x from U plus V has a unique decomposition x equals U plus V, with little u coming from U and little v coming from V. So the word unique is very important here. That's what makes the difference. Now if someone gives you subspaces U and V and asks whether their sum is a direct sum, that is not always as easy to test as it was in our examples 1 and 2. But here's a simple way to test whether a sum is a direct sum. This is a lemma, and it says that U plus V is a direct sum if and only if the two sets U and V intersect each other only in the zero element, which is of course as little as possible as two spaces can have in common. Okay, before we come to a proof, let's quickly check whether this test is helping on our first examples 1 and 2. So in example 1, the only vectors that are of this form, or maybe I should say of this form, and at the same time of this form, indeed is the zero vector. So the intersection of U and V equals 0 there, which indeed means you have unique decompositions, or in the sense of our definition, you have a direct sum. In example 2, well, the intersection is more than just a zero vector, because you have lots of vectors that are of the first and also of the second form. So here the intersection is the whole y-axis, if you want to say so. And that's why you get non-unique decompositions and you do not get a direct sum. Right. Okay, I think we are now ready to prove this lemma. And I always find this proof easier when I put the negative, so the opposite of every statement, on either side of the if and only if arrow. Okay, so if you can prove this equivalence, you at the same time prove this lemma. Okay, let's start with this direct. So we assume that U plus V is not a direct sum. Then some little x in the sum U plus V can be decomposed as U1 plus V1 and also as U2 plus V2, where the little u's come from U and are not the same, little v's come from V and are not the same. Okay, now let's forget about little x in the middle and let's just rearrange this equation into this equation by just subtracting the vector U2 from both sides and the vector V1 from both sides. And what we get is a vector on the left that is the difference of two elements from U, but U is a subspace, so again that is in that subspace U. Okay, and with the same argument on the right, you get a vector that is in V. And because of this equality sign, it's in both U and V. But by our assumption that the blue decomposition is different from the green decomposition of X, U1 is different from U2, and V2 is different from V1. So this vector we're talking about here is not the zero vector. Okay, but then starting at this assumption, we have arrived at this conclusion here. Right, let's try the other direction. So suppose that the intersection of u and v is not just the zero vector, but also contains other vectors. So let little w be a non-zero vector that is in the intersection of u and v. So w is in u, it is also in v, because u and v are subspaces. Also minus w is an element of u, but also of v, so it's also in the intersection. But that means that the zero vector can not only be written as 0 plus 0, but also as w plus minus w, which gives you a different decomposition from the first, because w and hence minus w is not the zero vector by our assumption. So indeed, decompositions are not unique, so u plus v is not a direct sum. Okay, and we have arrived here, which finishes the proof. Let us look at another, maybe not so trivial example. As our big and surrounding space, let's take L infinity, the set of all bounded sequences. And as subspaces, let's take U, which is the span of this element that I'll explain in a minute, and V be the set of all null sequences, which we denoted by C0. Okay, and this boldface 1 denotes the sequence that is constant 1, 1, 1, and so on. So the span of this element is just the set of all multiples of that element, which must mean the set of all constant sequences. Okay, and just to remind you, C0 is the set of all null sequences. Now let's look at the sum u plus v this time. What do you think? Is u plus v again the whole of the space X? Can every bounded sequence be written as a constant plus a null sequence? I don't think so. Well, maybe it helps to draw something here. So if we start with an element from u, which is a multiple of that constant 1 sequence, and the sequence little v coming from the set of all null sequences, then the sum of these two sequences will look roughly like this. So this clearly gives you a convergent sequence, and the limit is just the sum of the two limits. The blue limit was alpha, the red limit was 0, so this black sequence will converge to alpha. Okay, so every such element in capital U plus capital V is a convergent sequence. But of course, conversely, every convergent sequence can be decomposed into a constant sequence, which is constantly the limit again and again and again, plus a null sequence. So at the end of this argument, you can just write that U plus V is the set of all convergent sequences. Let's abbreviate this by little c. Okay, so the sum of u and v is something much more interesting now than in the previous examples. But is it also a direct sum? Well, we can just check whether it is subject to our tests from the previous lemma. So we only have to check that the spaces u and v intersect in nothing but the 0 element. But okay, this intersection contains all sequences that are constant and converge to 0. So this constant must be the 0, and therefore the only element there is the constant 0 sequence, which is exactly what we call the null vector, the null element in L infinity. So yes, it's a direct sum. And in particular, every decomposition of a convergent sequence into a constant sequence and a null sequence is unique. Good. Next definition, we say that the space that is given as our direct sum decomposes directly into U and V, and we call U and V complementary spaces of each other in W. Now it's very important to note that such a complementary space is not unique. Let's look at an even simpler example than we did before. The x-axis of R2 and the y-axis of R2 together give R2 as a direct sum. But the same x-axis can also span the whole of R2 in a direct sum together with maybe this subspace V here. So let's say this is the span of the vector 1, 1. Okay, so the same subspace U, which is the x-axis, has this subspace, which is the y-axis, as its complementary space in R2, but also that subspace, which is not the y-axis, as its complementary space in R2, because also here holds equality. And note that in both cases red and green only intersect at 0, so both are direct sums. Okay, so same red, different greens, so you have different complementary spaces for the same red set here.